So if one runs the script, there is a chance that you see just empty line and you cannot recognize what it is. And I'm going to explain the script line by line, but before doing this, let's immediately fix this little thing right away. So I'm putting the % sign after the plot command in line 37, saving and rerunning. And you see there is a, let me make it bigger. So there appears range, X range that corresponds to energies in electron volts, and we need to speak a little bit about units. Y axis is density of states, and there is a set of peaks that does correspond to individual eigenstates of the particle in three-dimensional box, which does experience confinement in all 3 dimensions. And you can identify visually the second peak is about 3 times bigger than the first one, right? Do you see it? So it can be, the interpretation is analogous to S and P orbitals in hydrogen atom. So there are 3 states, 3 degenerate states with the same energy, and they all contribute to the same peak. If one modifies the script and uses slightly different value of confinement in the each of 3 directions, so the box will look like a cube, but will be not literally a cube. You'll see that the second feature will, the degeneracy is lifted, and we see that it is 3 peaks together, right? So if the cube is not equal. The goal of our meeting is to manipulate the size of the box, see how the manipulation of the size of the box changes the density of states, and make a little report on, like make screenshots and then submit a report on that. Again, I'm going to systematically go over the script, but let me make a couple of things right away. So when we did have the meeting on the use of MATLAB for different purposes, there was one question: how to modify line thicknesses and font size, which is kind of basic thing, but it's if we need competitive figures, we may want to fix it. So there is a way to edit figure. So you click on the object, change the background white. Then if you click on the line, there is a way to change its thickness. Then if you click on the axis, there is a way to edit X, Y, and Z, so where you can modify the range limits and also the font. And huge fonts are considered as something good for better visibility, right? So now even with low quality display, or if it is transmitted via Zoom with some errors, it looks a little better. And also there is one thing: if you click more properties. There is general line width. If you change it to like 3 or 2, it makes the line thickness of the border a little better. And for the y-axis, it will look more beautiful if one starts a little below, so that we can see, so that range and the line itself do not overlap. So those are just little hints how to make beautiful, or I shouldn't brag, readable figures. So as we go through the class, please consider make screenshots and later place them into Word or PowerPoint for later submission as a homework. Feel free to stop me anytime and request clarifications if I'm getting too excited and forget to ask if you follow what is going on. Okay, so I don't know if you feel excited about the following, but I'm going to go line by line, same as we did in some previous time, and maybe you find it useful. If not, let me know. I'm considering it not as a pleasure, but as my thing I have to do. So okay, let's focus there. I'm going to focus on the board and maybe draw something if needed. Down and in. Up and out. Okay, yeah. Bottom of my screen. Did you get the script in the email? Oh, you were looking on this stuff, right? Okay. So Planck constant is set to 1. Mass of electron is set to 1 since we want to use atomic units. Conversion between atomic units to electron volts. So here is size of the box in X and Y direction. In atomic units. One day we will need to discuss about atomic units. They are needed, and we will use them for the project. And basically, those are the units where Planck constant and mass of electron are equal 1. So it is they're designed to make all equations simpler. So here is the range, in which range of energies where we explore density of states. Width parameter. So if we are looking on the images that are generated, this width parameter is something that defines how thick is individual line. It's not literally this 0.05, but it is related. If you want this line to be thinner, you put a smaller number. If you want it to be thicker, you put a different number. So if I make it 10 times smaller, lines are expected to become thinner. So we run. And now you see lines are very, very thin. And it already screwed up my thickness of lines. I need to redo it. And there is a way to do it in command line. We'll discuss it as well. So maybe it looks a little beautiful, more beautiful if you make them thicker. Now also line widths in atomic units, which we are going to use. Range of energies in atomic units. What? Width parameter in atomic units. Yeah, thank you. Grid points. So we split all range, see from 0 to 5 onto individual points. And this is needed because we are making connection between discrete and continuous representation, right? So when there are individual lines that we as humans can analyze, it is discrete representation. But if we will consider like thousands of states, it will be continuous, and we cannot look at the individual eigenstate. We will build the distribution same as in the class. And this 2000 steps is just telling how many points are along x-axis. You are very welcome to play and modify any parameters and record what you observe. Okay. So it is a size of distance between two near grid points in energy offset between nearest grid points. Grid points. Let me make a little demonstration. So Lola asked what are the grid points. So right now we are plotting the figure as set of as continuous line. So when each grid point is connected by a small line, if I put it as points, you see, well, probably you do not see, but it shows each line as a set of points. And maybe to make them visible, we can put little circles. So this line is represented by a set of points, and we can make them either denser or sparser, depending on whether we want fine resolution or rough resolution, right? And you can put both circles and line. Now they're connected by line, right? So this continuous distribution that we are going to draw is indeed consisting of individual grid points, but they are placed quite dense, quite close to each other, so that human eye will consider them as a continuous line. Make sense? So if you count number of circles here, it will be 2000. Okay, I'm just preparing to make this line. If I make them right now for this first peak, we have 1, 2, 3, 4, 5, 6, 7 times 2, about 14 points. Right? If I change the script if I change number of grid points 1000 instead of 2000, individual peak will be represented not by 14 points, but maybe by 7, right? Let's check, save, run. And now I will replot it. Let's return back to the small, yeah. And now if I replot it in this way, instead of 14 points, it shows 1, 2, 3, 4, 5, 6, and maybe 7. So it's same like high quality figure and low quality figure, number of pixels. Better? Make sense? So instead of grid points, you can say pixels. Okay, so same in atomic units. Here, this is something that you can replace by command line space, right? You set grid points from 0 to maximal energy with increment dE. And then here we declare the array DOS where we are going to place the data. If you are impatient and look back to the end, we will plot range, E range will be X, DOS will be Y, right? And in the line number 18, DOS variable is filled with zeros, but we are going to populate it later on. So scan quantum numbers for motion along X. There was a question right after the class today. As I understand, there could be a confusion for the word quantum numbers, because you have heard in the freshman chemistry, you've heard quantum numbers like principal, orbital, magnetic spin, right? Any number that specifies quantum state can be called quantum number. So here, the nx and y and z are quantum numbers that specify how vivid is motion in x, y, and z direction. So it's related to momentum, right? And if we have nx equals 1, 2, 3, it means more and more motion in x direction. So that it's not quantum numbers from freshman chemistry. It's like more general quantum numbers. Specific here it is for just linear motion in certain direction. And the energy for one-dimensional box has only one quantum number, and it is constant, quantum number squared, size squared, right? If we have three-dimensional, then instead of n, it should be 3 and x and y and z. And then again constant, and here it will be nx squared, lx squared, and y squared, ly squared, and z squared, lz squared. Make sense? So because we assume that motion in x, y, and z is independent. And before we practically compute these energies, when we just write down the equation, we do not need to know what will come out. And before we know exactly the size of the box, we do not know in which range of energies this eigenstate will fall. So we want to look on all values of this quantum numbers. So we want to explore the values of nx equal or bigger than 1, and then smaller than infinity. And same for ny and z. So we want to scan through all values. And because we are impatient humans and we want to get some answer quickly, we can just replace infinity with 30, which is quite a big number. But if you are curious what would happen if you want to increase precision of your code, you can put like 40, 50, and you will obtain more beautiful figures. Some errors will disappear, but you will notice that it will, instead of 1 second, it will take 2 seconds, which our human tolerance can admit. But if you put like 1,000, you will need to wait like a minute, which some impatient people cannot tolerate. So for learning purposes, we just put small numbers. And here we are scanning quantum number along x, along y, and along z. So next 3 lines are focusing on this equation. Even if you hate equations and do not like writing them, human brains, even if you are not motivated, are more powerful than any computer. And this equation, I do not think anyone feels too much upset of this equation. You do not consider it too complicated, right? If you just want to type it and into the computer code, we want to avoid mistakes and just make shorter lines. So one can consider this as a three components: energy contribution for motion along x, energy contribution for motion along y, energy contribution for motion along z. And we just type them separately with expectations that we will add them together. And then we add these energies together because it is a trick from math. If the motion along certain degrees of freedom is independent, then operators, contributions of operators and contributions of energies are additive, and wave functions are factorizable. So it is quite standard thing, and that works in many areas of science and engineering, and it's more if you go only from undergraduate studies, one may believe that this is typical every time. Sometimes there are exceptions, but they're so complicated that humans try to avoid them. So if motion along degrees of freedom is independent, then energies are added and wave functions are multiplied, as we see here. So those three things are added together, and those are energies that would contribute to the definition of the density of states. I'm going to erase this panel. So we do have a value of E and X and Y and Z. So energy of one of the eigenstates. Right now, we don't care what is the shape of the orbital, not because we really don't care, but we do not have enough time and energy to look on it. We are focusing more on energies. Now we are practicing the definition of the density of states, where we place a peak at such energies when our running variable is exactly equal to the energy of the eigenstate. And in order to get so dose of energy is summation of these delta functions, right? And since there are three quantum numbers, we have two summations. So now we can look back for the line 20, 21, 22. Here we scan these quantum numbers which would relate to these summations. Now, delta function is infinitely thin. And it's not good for us as humans to look. We better want to overlap several peaks and assign natural width. On one hand, it's just comfortable. On another hand, if we look into the nature, energies of like molecules change over time because molecules are being hit by other molecules from solvent, because our like support surface is vibrating, because there are thermal fluctuations and some uncertain factors, or because there are several molecules in an ensemble and each of them is in a different phase of motion. So there is some uncertainty in the energy, and this can be attributed to a width that we place into this delta function. So instead of delta function, we put same subtraction we place Gaussian profile, right? And this Gaussian profile depends on our range of energies, which is discretized through like 2000 grid points. And there we place all of these energies. So we will have as many of these Gaussian exponentials, as many quantum numbers we have, right? So each time I'm jumping through a couple of lines. So each time we pass through the cycle, we add new peak to our variable where we accumulate density of states. Each time we pass here, we add a peak, a new peak. New peak. to DOS. And now a couple of lines how to get this peak. So we set up the power of exponential, so which is called nom. That is power exponential. So it is offset between our energy range and eigenvalue squared and divided by width factor squared. And here one also needs normalization in front of exponential normalization. And then one adds together the normalization times exponential, and then one multiplies it by increment. So it's actually the peak. Okay, and here we are done. We just plot these variables as x and y, right? We can put thick lines are good, so one can add a command comma. Line width, comma 3 or 4. Let's check if it works. Save, run. So it doesn't appear immediately. Save. Maybe it doesn't like some of the line 22 column 23. So yes, it doesn't like my comments. Once again, save, run. So by now it draws a little thicker lines, which are better for report. And one can also in this labels, one can add font size. Let's check if it works. Save, run. And you see it makes a little bigger font, which is better. Otherwise, if you put it this little image, this little fonts will be invisible. Okay, so let me invite everyone to try running this script and check if it works. I will just approach and see if you can generate the figure and if you have some quick questions, and then I will after visiting everyone, I will keep the story further. Yeah. today doesn't want to switch between front and back camera. I hope to be able to focus on everyone. Okay, yeah, I think no specific questions. Okay, good. Sibyl, do you have the image? Okay. So let's just save and rerun. $37.17 line. Okay, so line spelled, and there should be a comma between those and line width. Save and rerun. It will work even without fixing this error. Let's. Okay, yeah, very good. Okay, any specific questions?
No, but what are we getting to the stuff that's supposed to?
Yeah, we will get to this at the last point. It's for making analytical way. All works? Yeah. Okay, yeah, thank you. Yeah, what? Because those are atomic units. So in SI units, it's very uncomfortable number, like 6 to the power 10 minus 30 something, right? Wait. Joule in SI system, Planck constant is joule times second. In the atomic units, it's like heart rate times atomic unit of time. But by resetting values of the constants, one can browse between different system of units, and atomic system of units is comfortable to those who need to write many equations. Because if you skip this h bar and mass, all equations become shorter and simpler. Let me invite those who are on the Zoom to share screen and just confirm that everything works. So I see Josh and Wyatt are on Zoom. Okay, Wyatt is sharing. Would you please show the image? Okay, yeah, excellent. Yeah, it works. Thank you. You can stop sharing. Joshua, would you please share? Would you feel comfortable to share your screen? Okay, and I am curious to see your the image, the figure that is being generated after running the script. Right now, you're sharing the screen with text of the script of the code. Can you swap to the figure window? Maybe.
Can you repeat that again?
Share the whole display as a single window, or just focus on the image window.
Command window.
So it's command window, and there should be a window with image.
Window with image.
This error will not prevent you from having a healthy. There should be another window with the figure.
With figure.
in some computer systems, you can jump between windows by simultaneously pushing Alt and Tab.
I'm a little confused.
Or you can just tell to the microphone if you see the figure in the way it should be, and then I will just believe you. Maybe consider to switching on the microphone. Or
Yeah,
typing
my
the chat line.
microphone's on,
Because
but
you
I'm
are
still a little
not
confused.
showing the image.
You can't see the image? I mean, I have the image up, but not sure why you're not
If you're
seeing.
interested, the best
See if
I would on your place, I would stop sharing and then
Right.
start sharing the whole
All right.
display, not a single window, but the whole display.
The whole.
Okay, perfect.
Yeah.
Yeah, thank you. You can stop sharing. You did it perfectly. Yeah, thank you. Okay, so let's return. So now please look on the lines 5, 6, and 7, and the goal is to select such 4 sets of these numbers that would represent quantum dot, nanowire, thin film, and infinite space. Infinite space would mean to put very big numbers everywhere, and please try your creativity in this little assignment. I don't want to suggest you specific numbers, just try to play with these numbers, rerun the code and see what happens. So this will be an invaluable experience that you could use later on.
Why does it do that at the end again?
So if you increase the number of the range of quantum numbers from 30 to, let's say, 40, this should change. So before I visit everyone, let me address a question. Okay. When a value of a quantum number increases, we get to a higher energy, right? When we are considering the limited range of quantum numbers, we access only shorter energies. And I will reproduce here the image of 2-dimensional quantum numbers that the straw man was exploring. So if our nx and ny are small enough, we are exploring slices that look like a part of a circle, right? But if our nx and ny are limited, and we are coming to the range, for example, this one, then it would be only a portion of the circular surface. And it will give some signal, will give some results at these energies, but it will be inadequate because it will miss the part of the picture. So beyond some threshold, which would correspond to the range where sphere can be placed inside of a cube. So beyond some threshold, it will give unreliable results. And therefore, if so, Nate went into the steps, and the range where it stops showing steps as it is expected for two-dimensional system, and it starts going down, it is this range where it is not circular anymore. And at some, when we completely went out of the cube, it will show 0. But there are reliable, unreliable, and absent, like 3 ranges. Make sense? Okay. Okay. So what's your goal by now?
So if I go lower, like for example, go to 25 and 21, we'll see the
Okay.
Yeah.
So I'll switch off the microphone that no one else knows this. Okay. Like seal. And if you have a successful run, I imagine your schedule is quite busy, so just make a screenshot and paste it into a report of Word file or whatever, so that you do not waste time later. Okay. Yeah, it looks good.
Is there any like? Because another thing I noticed is that when I tried to do like 2000, it would just go back to like those little peaks again.
2004?
In X and Y. Like, yeah, I'll show you.
Yep. Okay. Then confinement is too small and all picture is hidden in there. If you simultaneously increase this one proportionally, like 60, 60, 60, and here maybe instead of 2000 do like 400, and here like 60, 60, 60 in each, it will be equivalent. So it should be balanced between those. So feel free to play more and get some experience how the system responds to your trial experiments, and do not hesitate to make screenshots, because who knows, maybe you want to invest more time on, maybe you will be busy, and if you have screenshots maybe placed immediately into Word, your homework will be basically done. too heavy. Okay, so you're changing it in a like humble range. Try to keep ones small, like okay. Yeah, keep trying, but
This is big enough.
yes, let's see what happens. So it looks more like continuous. So you changed it about 10 times bigger, right?
Mhm.
This one is about 5 times bigger, and this is
Yeah.
2.5. What if you have all the three numbers same size, same big as the last one?
Okay.
Yeah. So here it looks more continuous, and there it drops because lack of this quantum states, right?
Yeah, so I think
So in the it drops because it is not enough quantum states.
Okay.
But up to this 1 electron volt, this figure, this picture is reliable. Okay. So just keep playing and maybe save images, and later on you'll select 4 best figures for. I know that you're auditing, but if you send homework, you help me to look what you are doing. Yeah, thank you. Wyatt may invite you to share screen. And Joshua, please prepare to share screen after Wyatt. I think Wyatt is either on the break or not ready to share screen. Joshua, would you like to share screen on your side? Oh, okay, how beautiful. So let's go to let's open your script. Yeah, this is a beautiful figure, but now you see that it is a superposition of many lines, and this fluctuations is because they have quite thin, quite narrow resolution. So if you change sigma 10 times bigger in the line number 9, so let's go to line number 9, remove one of the zeros instead of 0.005, yeah, save and rerun. Is it better?
Much better.
Okay. And let's try, yeah, just as an experiment in the lines 20, 21, 22, let's change 30, 30, 30 to 40, 40, 40,
All
just
right.
as an experiment. Save and rerun. So you see this trend of increasing density of states holds for a larger range of energies. And if you do like 50, 50, 50, it will be up to the almost for the whole range you're exploring. So Joshua, please consider to make screenshots of your images, and later on copy paste them into Word, Microsoft Word or PowerPoint files for the report. And right now, the values of Lx, Ly, and Lz quite similar to each other. They're of the same order of magnitude. But for example, if you want to do one-dimensional box, like a tube for a picture, it is very big in one dimension. You can keep Lz equals 300. And in X and Y, it should be much smaller. So it should be smaller, not like 2 or 3 times. It should be smaller, like 10 and 20 times. Let's try to do Lx and Ly equals to like 10 and 20. Save and run. What do you see?
Have like a
Does
bunch
it
of
look
the
like 1 over
let's
square
say
root of
sails.
energy? Does it look like a seal for ship? I think you're in a very good standing, so you can stop sharing and keep exploring, but don't forget to make screenshot and save it into your Word file. Okay. Interesting. So wait, sigma is too big. Yeah, now let's redo. Okay, now let's go to line 21 in the script and make it like 40, 40, 40, or even 50, 50, 50 to expand the range. It will, yeah, and we run and let's open the figure. So yeah, so approximately up to 2 electron volts, it looks reliable. It reproduces the expected steps. And after it starts giving errors. Let's look once again on the way where you define the lengths. So the value of 450 in line 6 means that your object, your box is quite big and confinement doesn't play so important role. So it shrinks energies to a narrower range. Let's put 200 or 250 or 300, like 200, yeah. And now we run and see what happens. So now it reproduces the steps almost for the whole range, right? And
yes.
now you see that Lx is small and Ly and Lz are quite big. So it is thin in one dimension and large in 2 other dimensions. So it's like a pizza box, thin layer. To have all assignments completed, we need totally 4 quantum dot when it is small size, big confinement in all 3, and then have this small and big number in different combinations. So you are in a very good standing. Please, you can stop sharing and keep exploring as you do, but don't forget to make screenshots and save them, paste them into Word file for the report. Yeah, thank you. Okay. So basically, you have several parameters you can modify: sigma and x and y and z, and its secondary and primary parameters are Lx, Ly, Lz. And for small, big confinement, we can call it zero-dimensional quantum dot. Lx, Ly, Lz are all small. So Lx, Ly, Lz, all three tend to 0. And our value of 20 is approximately 0. It's well, smaller. We cannot, if you look for real systems, we cannot make an object of the same chemical composition smaller than a certain size. Then it will be not symmetric and will break its composition. Then if you want one-dimensional, we will have Lx, Ly tends to 0, and Lz tends to infinity. But from your practical experience, you see that if you really make like 2000, it will be no confinement and everything will be squeezed to very small energies. So be prudent and big, but not super big, maybe 10, 20 times bigger than original value. Then if you need two-dimensional, then you're like one of the values is small, like Lz gets to 0, and then Lx, Ly tend to infinity. And then for three-dimensional box, all three go to big number. Right? So there are some questions that you can ask yourself and answer in your report. For example, why there is 0 and like density of states is 0 until the first peak appears, and this 0 range is visible almost in all runs, in all experiments you do. What controls this value? So the question is quite easy, but if you try to verbally address it, it just gives you experience how to operate with these concepts. And I'm going, okay, we are doing well in time. I'm going to show in script, at least I'll try how to match the computational results with theoretical one. But while I'm doing little preparations, maybe just accumulate enough figures for your report. Okay, so let me attract your attention. So x-axis is energy, and then as we predicted in the class, for three-dimensional case, it is square root of energy, right? So square root of just energy to the power 1/2. One can combine the constants when we perform this integration and compute this constant analytically, but right now we just need a proof of concept, and one can just fit this constant that they look similar and get the agreement of all functional shape. So if we try to fit the computed density of states with square root of energy, you see that until certain range it agrees really well. So it is a sort of a proof that when we did our exercise in class, we didn't make any serious errors. So if you can try do the same fitting and place it into your report if you want to. Okay, I think if you have got all four figures in the same style as in the class, let me check. So if you got figures of the all four shapes, please feel free to disconnect or depart. If your images slightly differ from it and you want to get more experience, I'll stay here and answer questions and help practically. But there will be, I wasn't planning any more additional instructions. If you need to go, you're welcome to do so. If someone is very curious after you're done, I can, if there will be demand, I can share the script for the movie that we did at during the class. But just to try, it may not work right away, but if you have curiosity, you may debug it for your pleasure. Okay, is anyone ready to go, or who is planning to stay? No one? Okay, so then meeting is done. I'll stay here to answer any questions, but feel free to depart in peace, and looking forward to see you on Friday. Have a nice, hopeful, relaxing evening. Why, do you have any questions?
Could you share the
Do you want
screen
me to
with the code on it one more time?
It looks like you are speaking, but I do not hear. Maybe your microphone is on, but sensitivity is low. No, you are muted.
Could you share the screen with the code on it one more time?
Still. Same system. No, I don't hear. But you can type if you let. Could you share the screen with the code on it one more time? Yeah, sure, we'll do. We'll do. Oh. And let me know if you want me to scroll it up or down.
You still can't hear me, right?
Can't ready. Okay. Yeah. Wait, would you please show the value of X, Y, and Z? It's like lines 6 and 7. Let's put LZ equal to 300 or whatever. Just add, yeah, save and run. You see, it's better, it's closer. And now, if you you can modify either values of X, Y, and Z, or better, just at the bottom, remove this multiply by 2.7 or multiply by just 0.7. Okay. Save and run. And since we are fitting, it looks like it should be 0.65. It will be almost 60. I would say 0.5 was now the line will be still below. So something between 6 and 7. Okay. Yeah. Excellent. And it could be like figure number 4 for the whole. Is there anything else you would like to talk about? Maybe just type. Okay, then I suggest we announce the adjourn and see each other on Friday. Okay, yeah, thank you. Thank you for exploring it in a meticulous way. Feel free to disconnect.